It's the mid-90s. The dot-com boom is just starting to take off. Tyson is gearing up for his comeback, and the Swedish company Geotronics has just added a novel feature to their flagship theodolite that will drastically change the future of land surveying. What a wonderful time to be alive. If you're watching this, there's a good chance you've used a robotic total station before, and if you haven't, you've probably seen one operating. And if you're like me, you've probably wondered what kind of wizardry is behind this piece of equipment where it can track a surveyor automatically. Well, that novel feature that changed everything is called automatic target recognition, or ATR. ATR essentially allows robotic total stations to lock onto a surveyor's prism and follow it around by manipulating small motors inside of the instrument that control the axes of the total station so that the telescope will point at the prism with astonishing accuracy. Today, robotic total stations are the predominant total station of choice over their manually pointed counterparts because they can drastically increase productivity. But do we surveyors that use this technology every day fully understand how it works? Today, we're going to explore exactly what ATR is, how it works, what are the accuracy implications of using it, and most importantly, how do we make sure we're using it properly? Because if we aren't, it can have detrimental consequences on our data. If you use a robotic total station, you're not going to want to miss this one. It goes by many names depending on the manufacturer of the total station: ATR, Autolock, X-trac, focusing system, or auto pointing, to name a few. But regardless of who made the robotic total station, the ATR system essentially operates the same way. It emits an infrared laser beam, typically out of the objective lens, that is reflected by any round or 360-degree survey prism, and that reflected laser beam then passes back through the objective lens and is diverted onto either a CCD or CMOS sensor depending on the instrument. Both CCD and CMOS sensors achieve the same task of accepting, capturing, and converting light into electrical signals, in this case as a light spot that is used to represent the location of the prism relative to the optical axis or crosshairs of the instrument. The ATR algorithm then evaluates the characteristics of that spot to make sure it's an actual survey prism and not the surveyor's vest or a traffic sign reflecting the emitted laser beam. If that reflected prism spot is too far from the CCD sensor's zero or central reference point, the ATR system tells the robotic total station's motors to adjust where the objective lens is pointing until the reflected spot is close to being on the center of the CMOS or CCD sensor, and thus the center of the prism is lining up with the center of the telescope, more or less. Once the reflected spot is close to being centered, the deviation between the calculated center of that spot and the center of the optical axis is calculated and combined with deviations calculated by the angular and inclination sensors within the total station, and a final horizontal direction and vertical angle are calculated. To put it simply, the ATR system takes a picture of the prism you're pointing at, calculates where the center of that prism is relative to the crosshairs, then applies that offset to the measured angle directions. Now, if you've ever looked through the telescope after ATR has locked onto a prism, you've probably noticed it isn't pointed perfectly at the center of that prism. This is because, to save time, the total station approximately points at the center of the prism, then calculates the remaining horizontal and vertical offset between where the telescope's crosshairs are pointed and what the ATR system thinks is the true center of the prism. So why do we bother using ATR? We often survey in two-man crews. Why not just have one person manually aim the instrument and the other person hold the prism? Well, we can do it that way and have done it that way for hundreds of years, but being able to precisely point the total station and hold the prism at the same time means we can free up one person to take care of other tasks. In certain cases, we can effectively double our production this way. Besides increasing productivity, we can also increase accuracy. Now, this is where things start getting debatable. Tell an old surveyor that's refused to switch to a robotic total station that manual pointing isn't as accurate, and I wouldn't be surprised if you got some pushback. And there may be some truth to that. Right about now is the time I would usually suit up and head out to the field for some testing. But unluckily for me and luckily for you, there have been some amazingly well done studies on this subject with testing methodology so rigorous I just don't have the time or means to replicate them if I wanted to. Let's start off with a study completed by Wang, Maohua Liu, and Fang Liu out of the Shenyang Zhangzhou University. 6 different sets of tests were conducted, each designed to test various influences on the precision of the total station's distance and direction measurements, both when using ATR and when manually pointing the instrument. The variables tested were distance from the instrument to the prism, observation time throughout the day, sighting through different obstacles, varying sun angles, sighting over various terrain conditions, and using different zenith angles. The entire testing scheme included 33 different sets of observations, and each set included no less than 10 measurements, with the mean square error being calculated for each set. A Leica TS30 was used, which has now been succeeded by Leica's TS50 and TS60. There was no mention of what prism was used. The intent of the study was to gauge under what conditions the precision of the total station would be better, either using ATR or manually pointing the instrument. Right off the bat, the testing revealed the precision of the EDM was not influenced by use of ATR or manual pointing, and none of the variables tested had any significant impact on EDM precision. Even when taking observations through glass, leaves, bushes, or a wire fence, the distance, mean square error, was not significantly impacted. Now, this was actually somewhat surprising to me at first, because I know firsthand that when I do make observations through vegetation, for example, I will get some outliers in my derived coordinates. That's one of the reasons I like to take repeated observations if I have an obstructed sightline, to detect and remove these outliers. But as we look at the results table for the test that included making observations through obstacles, we can see there is in fact a decrease in precision, but it comes at the cost of direction measurements, not distances. So this study indicates that the outliers we often see when dealing with an obstructed sightline are due to erroneous angle measurements. And as we examine this table further, we can see that ATR performed worse than manual pointing when dealing with vegetative obstructions. The author noted that as the level of obstruction covering the view of the prism increased, the precision of the ATR decreased, which makes sense now that we know how ATR works. If that reflected spot on our CMOS sensor has artifacts in it, it stands to reason the center of the spot that is calculated could be done so more accurately had those artifacts not been there. So does that mean we're better off manually pointing our instrument when we need a high level of precision? Not always. The ATR performed worse in these specific 2 conditions. What about the other 31? Well, in every single other one of the 31 conditions tested for, ATR performed significantly better than manual pointing, sometimes by as much as a 4x increase in precision when using ATR over manual pointing of the instrument. Another very interesting aspect of this study was the influence distance from the total station to the prism had on the measured direction precision. There was a reverse parabola of the direction mean square error when using ATR, where the most precise direction measurements were made at 50 meters. The direction precision was twice as bad at 100 meters and 4 times worse at 200 meters and more than 8 times worse at 750 meters. So what's causing this? Well, as the prism gets further away from the total station, the reflected spot on the CMOS sensor gets smaller and smaller, which means it makes up fewer and fewer pixels. If you've ever picked GCPs from aerial imagery before, you know that it's much easier to define the center of a target when you fly lower because there are more pixels contained within that same target, or in other words, it's of a higher resolution. It's the same sort of idea here. When we have a spot size made up of only a few pixels, there is more opportunity for a miscalculation of the center of that spot. And of course, some total stations do have higher resolution CCD or CMOS sensors that is supposed to help with this issue. Generally, newer and more expensive instruments have a higher resolution sensor. Now, it's difficult to say that just because this Leica TS30 saw these deviations, all robotic total stations would see deviations of an equal magnitude. The Leica TS30 used Leica's older version of ATR, named simply ATR. The newer generation of total stations from Leica, such as the TS50 or the TS60, now use ATR Plus that incorporates an improved CMOS sensor and algorithm, and in the white paper titled ATR Plus, written by David Grimm, Gerard Kleemeyer, and Hans Martin Zog, there have been significant improvements with the newer generation of ATR. Regardless, this is still extremely interesting to me, and I believe the principles seen behind the degradation in precision will still hold true regardless of which ATR system you're using. I often wonder at what point does it make sense to split up one long traverse leg into multiple shorter legs if line of sight isn't an issue. Of course, we can't only use these values alone or even the values determined from a specific instrument you're using and say 50 meters is the optimal traverse leg because, for example, if we break up a 100-meter leg into two 50-meter legs, we are introducing another setup which brings with it all the additional random error sources that comes with adding in another setup. Target centering error, instrument centering error, EDM error, so on and so forth. You would need to determine what effect distance has on ATR directions for your specific instrument, then sit down and do the air propagation to figure out the optimal traverse leg distance, taking into account that this study is indicating that pointing error isn't a static value when using ATR as we so often assume. A topic for another video perhaps. The next study we'll look at is a bachelor's thesis from Mr. Ashley Weyman-Jones out of the University of Southern Queensland. The intent of this study was to gauge how different obstructions affect ATR's ability to correctly define the center of prism. The obstructions he tested for were construction shade cloth, glass, vegetation, a dusty objective lens, and water droplets on the objective lens. All obstructions were tested on both the Leica GPR1 round prism and a Leica GRZ4 360 prism using 3 different total stations from 3 different manufacturers. Ashley noted that there was no significant difference in precision between the 3 total stations tested when sighting prisms that were either obstructed or unobstructed. What was quite surprising to both Ashley and myself when reading through the data was when there were no obstructions, the GRZ 360 prism performed better than the GPR1 high precision prism. I don't have a clear explanation of why this was the case, and it goes against quite a few other studies I've read and even what Leica would say you should expect from these prisms. There was no mention if this was a new GPR1 in the study, and part of me suspects it's possible there was an issue with the particular GPR1 that was being used in the testing scheme. It's important to note that this finding is unusual and should not be taken as an endorsement of the GRZ4 over the GPR1 when high accuracy is desired. Nevertheless, there is still plenty of valuable information that can be concluded from this study. Ashley found there was a very consistent trend of the precision of the direction measurements to the 360 prism being impacted much more than the measurements to the round prism. That is to say, when there were obstructions that degraded direction measurements, the 360 prism was impacted more than the round prism. He also found the closer the obstruction was to the total station, the larger the negative impact was on precision. And lastly, he concluded having either a dusty or wet objective lens had little negative impact on ATR precision. The third study was performed by Jaroslav Braun out of the Czech Technical University of Prague. The intent of his study was to determine the precision and accuracy of ATR when using reflective targets. The testing of reflective targets is starting to get out of the scope of this video, but in addition to making measurements to reflective targets, he also included a GMP 101 prism and compared the precision of measurements made to that using both manual pointing and ATR at varying distances. Like the study out of the Shenyang Zhangzhou University, he also found a significant increase in precision when using ATR versus manual pointing, in the range of 4x depending on the distance between the total station and the prism. I decided to include this because a completely different study using completely different methodology backs up the findings that ATR does indeed increase precision significantly versus manual pointing of an instrument. Another interesting finding from this study was that ATR was also fairly precise at locating the reflective targets with variances of around 0.5 millimeter, but the accuracy of those targets had errors of 0.5 millimeter up to 2 millimeters. Remember, precision and accuracy are two very different things, and it's easy to conflate the two. Precision is a measure of the spread of a series of measurements, whereas accuracy is how far away the mean of those measurements is from what can be considered a true value. They also noted that as the angle of incidence to the target increased past 30 degrees, precision and accuracy were significantly affected. I've been talking about the effect angle of incidence has on reflectorless measurements for quite a while, and this is just another example of some testing to back that up. Yet another reason why I very rarely use reflectorless targets anymore and opt for Rothbucher's one-point-fits-all system. If you're still doing resections off reflective targets, do yourself a favor and check out Rothbucher's products. Remember at the start of the video when I mentioned that old surveyor that may be stuck in his ways of using a manual total station because of accuracy issues? And how I mentioned he might be right? Well, we already looked at one example where manual pointing could be more precise, taking measurements through vegetation, but there is another very pronounced situation where we could all be adding in a heap of systematic error to our direction measurements when using ATR. And the scary part of this error source is that it cannot be compensated for by dual face measurements. I'm referring to a miscalibration in the ATR's internal CMOS or CCD sensor that affects its ability to correctly determine the offset between the CCD 0 point or the optical axis of the total station and the center of the calculated spot on the sensor. We can think of it as a kind of collimation error, not too dissimilar to the horizontal and vertical collimation error present when manually pointing the telescope of the instrument, but this isn't an angular error per se. However, it does affect our angle measurements. It's a systematic error related to the sensor itself and how it interprets the prism's location relative to the instrument's crosshairs. Horizontal collimation error, vertical collimation error, compensator index error, and tilting axis error are all removed by dual face measurements, but that pesky ATR calibration residual error will still be left behind. This is why it's extremely important to calibrate your ATR system and calibrate it well in order to reduce the ATR calibration residual error as much as possible. If you rush to perform a horizontal collimation calibration, it's not the end of the world because if you want to ensure high accuracy, you should be dual facing your measurements anyways. And when we do that, it removes the systematic component of the manual pointing collimation error. Our collimation calibration could be multiple degrees out, and theoretically it wouldn't matter if we did dual face measurements. But any error left over from a poor or out-of-date ATR calibration sticks with your measurements until you fix the calibration. I should also note that if your total station has been fully field calibrated properly, including a compensator calibration and both a horizontal and vertical calibration, then you should be able to obtain single phase measurements free of the systematic error sources these calibrations are designed to compensate for. However, the benefit of redundant measurements and their effect on random error will still remain. I should also note that a miscalibrated ATR will have an equal effect on all horizontal directions made when the instrument is in that state. And since a horizontal angle is the difference of two directions, and if each direction is affected equally by the miscalibration, then the miscalibration is canceled out when the horizontal angles are determined using ATR. So you could run a traverse, and if you only used ATR and never manually pointed, the miscalibration in ATR wouldn't affect your calculated horizontal coordinates. However, if you started taking reflectorless observations mixed in, or any observations where you're manually pointing, you would run into issues. And more importantly, since a vertical angle is the difference of one vertical direction and the measured direction of gravity at that location, the miscalibration is not canceled out and does affect your calculated elevations. The ATR calibration is to be done in addition to the horizontal and vertical collimation calibrations and the rest of the field calibration steps, even if you only plan on using ATR and never manually pointing the instrument. The collimation corrections are correcting for non-perpendicularity in the actual instrument axis to adjust the optical center of the line of sight, and then the ATR calibration works on top of that and is adjusting for the now adjusted optical center of the line of sight and the center of the prism determined from the CMOS sensor. When we calibrate our ATR system, we do so by running through a routine in our field software that allows us to take a number of measurements to a prism using manual pointing, then a number of measurements using ATR, and the difference between the average of the two sets of measurements is calculated, and the horizontal and vertical components are applied to future measurements. When you're running through your ATR calibration routine, try to do so on a day when it's overcast or there is minimal heat waves, the temperature is about average for that season, and you've let your total station acclimatize and your tripod settle. Make sure your optical parallax is adjusted properly. A tip for this is to hold a piece of field paper in front of the lens while you adjust the focus of the crosshairs. This will give you a white background for maximum contrast. If your field software allows for it, take multiple measurements when running through the calibration process and make sure you're moving the crosshairs off the prism center and back on between each manual pointing. It's recommended to use a full-size prism over a mini and use a round prism over a 360, even if you're planning on primarily using a 360 afterwards. Now, if you're in the field and suspect you may be dealing with some ATR calibration issues, there is a relative easy way to check your ATR calibration. Take a dual face measurement by manually pointing the instrument at the prism and calculate the average direction. Then take a dual face ATR measurement on the same prism. Calculate that average and compare the two averaged directions. They should be within a second or two of each other. If you aren't, run through the ATR calibration and repeat this same test again. Since starting this channel just over a year ago, I've had the amazing opportunity to speak with and gather advice from some of the best minds our industry has to offer. It has hands down been the most rewarding part of making these videos, and this one was no exception. I was lucky enough to get in contact with a retired Leica Geosystem support engineer out of Sweden that was extremely generous with his time and helped guide me through the research portion of this video for no other reason than to get the word out there on how important this topic really is and pass on part of the wealth of information he has gathered over the years. A sincere thank you, sir. When explaining how the ATR system works, I purposely gave a simplistic explanation, and in reality, there is a lot more that goes into a modern ATR system besides looking at the reflection of a light spot, and calculating where it is relative to the instrument's crosshairs. There are many factors that influence how that reflected spot shows up on the CMOS sensor. Is the prism really close to the total station? Are you measuring through obstructions? Is it foggy out? Is it raining? What's the size of the prism being used? If a 360 is being used, are you looking at it head on or catching the edge? So on and so forth. And ATR algorithms and sensors have improved a lot over the past 30 years. I'm sure I'm not the only one that's been plugging away on a topo and autopilot, then looked down on my screen and wondered why the last 5 shots I took were all in the exact same place, until I realized my robot was locked onto someone's taillight or a stop sign. Luckily for us, with each new generation of total station that is released, there are often improvements made on the ATR system, better sensors and better algorithms. We're now at a point with the newest generation of robotic total stations that there is probably very little ground to stand on if one wanted to make the argument that manually pointing a total station is either more productive or more accurate. If, and this is a big if, the ATR system has been calibrated properly. All too often when I ask someone when the last time they calibrated their ATR system was, and I get the reply, "You can do that." You can and you must if you're chasing high accuracy work. If there is a single takeaway from this video, it should be calibrate your ATR system and check it often. The consequences of assuming it's fine can be the difference between meeting your spec or having to redo a traverse or worse. Well, that wraps up another one. In my next video, we're going to take another look at survey measurement adjustment using microsurvey's StarNet. We'll recap why we adjust survey data using least squares, how to run through a project start to finish in StarNet, and I met with some of the folks over at Microsurvey to get some hot tips and tricks we're going to cover that will have you adjusting your survey networks like a pro. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.